Tonight I want to talk to you guys about mixing problems. We covered cooling problems when we covered 4.2 in class before the first exam, but I saved mixing problems until after our first exam, which should have been tonight. In mixing problems, we have a salt water solution with a given concentration being added at a specific rate to a tank that already has some volume and concentration of salt water. So the solution being added may or may not have a higher concentration than what's already in the tank. And then the liquid leaving the tank will contain a mixture of the two. We want to determine the quantity of salt in the tank, which we will call Q of T, as a function of time. To simplify our calculations, we're going to assume that the solution coming into the tank and the solution that's already in the tank are being mixed instantaneously and continuously so that the mixture is evenly distributed throughout the tank. To begin building our model, we need to start with figuring out how to find the rate of change of the amount of salt. So we can find our rate of change of Q of T by taking the rate at which the salt enters the tank minus the rate at which the salt exits the tank. That will be our Q prime of T, or dQ dt, which is our rate of change in the amount of salt over time. The way we're going to find it is we're going to take our flow rate times the concentration. And if the concentration is not given, we'll take flow rate times the way we'll find concentration, which is the amount of salt in the tank at any time t, divided by the volume of water in the tank at any time t. What you're going to find is that when we have the given tank and what's in it, it will often be given to us as the amount of salt and the volume of water and not as a concentration. So let's look at a couple of examples. So I skipped over examples 1 and 2 because those were our temperature cooling problems with Newton's law of cooling that we did in class last week. So that's why it says example 3. But example 3 says a tank initially contains 40 pounds of salt dissolved in 600 gallons of water. Starting at T naught equals 0, water that contains 1/2 pound of salt per gallon is poured into the tank at the rate of 4 gallons per minute, and the mixture is drained from the tank at the same rate. Find a differential equation for the quantity Q of T of salt in the tank at any time where time is positive, and solve the equation to determine Q of T. And then we're going to find the limiting amount of salt in the tank. In order to solve this, we're going to need a little bit of space. So let me make our slide small and move it up and out of the way. So the first thing we're going to need is we're going to need a picture. All of my favorite problems start with a picture. So here I have a tank, and it's got a pipe coming in, and it's got a pipe coming out. And inside my tank, I have some solution. In example 3, a problem says that our tank initially contains 40 pounds of salt. So we have 40 pounds of salt in 600 gallons of water, right? And it says starting at T naught equals 0, water that contains 1/2 pound of salt per gallon is poured into the tank at a rate of 4 gallons per minute. So we're coming in, we know we have 1/2 pound per gallon at 4 gallons per minute, right? And then it says the mixture is drained from the tank at the same rate, which means the rate going out would be 4 gallons per minute, but we don't know at what concentration, or pounds per gallon. So let's start talking about our rate in, which would be the 0.5 pounds per gallon times the 4 gallons per minute. Our gallons cancel out and we're left with 2 pounds per minute is our rate at which the salt is entering the tank. Our rate out then would be some volume Q over how much is in the tank, which is our 600 gallons. That's how many pounds per gallon is leaving the new concentration, and the tank always has 600 gallons of water. Our new concentration would be Q, some number of pounds of salt, over the 600 gallons that are in there. And we're going to be multiplying that by its rate, which is the 4 gallons per minute. And I realize I wrote gallons twice. Sorry about that. So in this case, then, we end up with Q over 150 pounds per gallon. So our total rate, which is our Q prime, is going to be the rate in minus the rate out, or 2 minus 1 over 150 Q. Well, now we have a differential equation. Q prime equals 2 minus 1 over 150 Q. So if I bring it over, I then get Q prime plus 1 over 150 Q minus 2 equals 0. And if I multiply through by dt, right, because this is dq dt, we end up with 1 over 150 Q minus 2 dt plus dq equals 0. And I find that my m sub q is 1 over 150, and my n sub t is 0. So it's not exact. So we need to find our integrating factor. So our integrating factor P of t would be m sub q minus the n sub t all over n, or 1 over 150 minus 0 over 1, which is just 1 over 150. So our integrating factor is going to be e to the t over 150. Right? I'll leave that to you to work out that integration, which is pretty straightforward. So when we multiply it through, we end up with, let's see here, 1 over 150 Q e to the t over 150. Right? All of that is times, minus 2, I forgot the 2, minus 2 e to the t over 150. Right? All of this is times dt plus e to the t over 150 dq. Right? So from there, we can say, well, then I know that f sub q was e to the t over 150, which means that f of t q, when we integrate the partial of f with respect to q, we end up with q e to the t over 150 plus some phi of t that could have existed. So then we need to take the partial derivative of this one with respect to the other variable, which would be t. So let's find f sub t. The partial of f with respect to t would be q over 150 e to the t over 150 plus phi prime of t. And when we set that equal to the m, our mu times m, should say, we end up with 1 over 150 q, or q over 150, e to the t over 150, minus 2 e to the t over 150. So those are on both sides, and I'm left with phi prime of t equaling negative 2 e to the t over 150. So that means that phi of t came from a negative 300 e to the t over 150. If we plug this back in, we find out then that f of tq then equals q e to the t over 150 minus 300 e to the t over 150, which is also equal to c. We also know at the very beginning that at time 0, there were 40 pounds of salt in the tank. By plugging in our initial condition, we can solve for c, which is negative 260, and we find then that our q of t will be 300 minus 260 e to the negative t over 150. So there is our final model for this specific tank. So the limiting amount of salt in the tank as t approaches infinity would end up being 300 pounds. So the answer to part B would be 300 pounds. Hopefully you were able to follow along with this one. We're going to try one more just in case. For this example, we have a tank that initially contains 1 pound of salt dissolved in 100 gallons of water. Starting at T0 equals 0, water that contains 1 pound of salt per gallon enters the tank at a rate of 3 gallons per minute, and the well-stirred mixture leaves the tank at the same rate. Find the amount of salt in the tank at any time t. I'd like for you to pause the video and try this on your own before you come back and see how I've done it. So I'll give you a moment to consider that. And now we'll solve it. So we have our tank again, right? So our tank with some pipe in, some water and salt already in it, and a tank out, or pipe out, sorry. So in our tank, we already have 1 pound of salt dissolved in 100 gallons of water. At T0, we know the water that contains 1 pound of salt per gallon is coming in. So we have 1 pound per gallon at a rate of 3 gallons per minute is coming in. We know that it's also leaving the tank at the same rate of 3 gallons per minute. We just don't know at what concentration or what pounds per gallon. So when we start talking about our rate in and our rate out, our rate in ends up being 1 pound per gallon times 3 gallons per minute, or 3 pounds per minute. Our rate out then will be some volume of salt and some proportion in proportion to the 100 gallons of water and solution already in the tank times the rate that it's going out, or our 3 gallons per minute. So we end up with 0.03 Q pounds per minute going out. That makes our total rate Q prime equal to the rate in, which is 3, minus the rate out, which is 0.03 Q. And now we have a first order linear differential equation. And we know how to solve this. So the first things first, we're going to check to see if it's exact, and if it's not, we're going to use an integrating factor. So when we rearrange our terms and bring them over, we end up with 0.03q minus 3 dt plus dq equals 0. So now we need to check for exactness. M sub q, or the partial of m with respect to q, is 0.03. The partial of n with respect to t is 0. So it's not exact, which means we need to find an integrating factor. So our integrating factor starts with finding p of t, which is mq minus nt, over n, which just ends up being 0.03 minus 0 over 1, or 0.03. That makes our integrating factor, mu of t, out to be e to the 0.03t. Multiplying that through, we end up with 0.03 qe to the 0.03t minus 3e to the 0.03t, all times dt, plus e to the 0.03t dq. And now we need to start integrating. And we can see that this is exact by taking the derivative with respect to q of m and the derivative with respect to t of n. And they would end up being the same thing. Because the derivative with respect to q of m would be 0.03 e to the 0.03t. The derivative of n with respect to t now would be 0.03 times e to the 0.03t. So we can now solve it as if it were an exact equation. So I'm going to move over here to do that. So it's going to be easier to start with f sub q, which is our n, which is e to the 0.03t. If I integrate that partially with respect to q, I find that f of tq then is q e to the 0.03t plus some function of t that we don't even know what it was, because when we would have taken a derivative with respect to q, it would have disappeared. So now that we've integrated with respect to q, we need to now take the derivative, the partial derivative with respect to t. So let's take the derivative with respect to t, the partial derivative, and we end up with 0.03 q e to the 0.03t plus phi prime of t. And this now has to equal our mu m, which is 0.03 q e to the 0.03t minus 3e to the 0.03t, which means, oops, didn't mean to erase that, sorry, which means that phi prime of t has to equal negative 3e to the 0.03t, which leads us to find that phi of t was a negative 100 e to the 0.03t. Now that we know that f of t q is q e to the 0.03t minus 100 e to the 0.03t, and we know it's equal to a constant, we can look at our initial condition, which said, how much salt did I start with? I started with 1 pound, right? That comes from right here, this 1 pound. In fact, let me put it in a different color. This right here, that's my Q naught, or my Q of 0. That's my 1 pound. So when I plug that in and I solve for C, I end up finding that C equals negative 99. And solving for Q means that I find out that Q of T is actually 100 minus 99 e to the negative 0.03 t. And if I wanted to find the limiting amount as t approaches infinity, our limiting amount of salt in this tank would be 100 pounds. So I hope that clears up any confusion some of you may have had about how mixing tank problems work, and I hope it makes it very clear to those of you who are new to mixing tank problems how these work. A lot of it is just sitting down, looking at what's already there, what's coming in, and what's going out, and finding a way to organize them in a way that you can figure out, well, if I want to model this, I need to know at what rate it's changing. And I can find that by taking the rate in minus the rate out. And the rate out, we don't know how much salt is leaving, so we have to use it in proportion to how much solution was in the tank when it was coming out. And when we do that, and then we take our rate in minus our rate out, and we put them together, we find that we have a first order linear differential equation, which we can then solve with the tools that we've already learned in class, and we can come up with an equation to model our mixing tank problem. So I gave you 3 homework problems for this section. They are problems 7, 9, and 11. And I know 9 and 11 are both mixing tank problems, and number 7, I believe, is a cooling problem. So I also want to warn you that the web work assignment for this section is 5 or 6. I lost my paper somewhere on my desk. 5 or 6 problems that are all mixing tank problems. So you're going to get a lot of chances to practice mixing tank problems. I will also remind you that I will be covering mixing tank problems on exam 2.